Hello my dear students. So I am going to continue with the lesson. In the previous two chapters, we discussed how we can prepare gases. We discussed their properties as well as their uses. So in the previous chapters, I discussed with you all how we can collect hydrogen gas and oxygen gas in the laboratory as well as their properties and uses. So now the third gas, that is carbon dioxide. So when we say carbon dioxide, you are familiar with the molecular formula CO2, carbon dioxide. And this is present in atmosphere as well, but in a very small percentage. You all can remember, students, we have discussed the composition of atmospheric air. What is the gas that is present in highest percentage? 78% of nitrogen. Then there is oxygen, 20%, and carbon dioxide, it is only 0.03%. So carbon dioxide is a gas that contributed to the advent of life on Earth. Although it is present in just 0.03%, it is very important for life on Earth. So that is why we say contributed to the advent of life on Earth. You are familiar with these processes also. Now, all the living organisms, they need energy. How do they get their energy? They get it from food. So when we say food, food has to be produced by plants. And that process is what we call as photosynthesis. And carbon dioxide is a raw material for photosynthesis. So therefore, it is very important. Then when that is converted to glucose, organisms, they all consume food. Again, that glucose undergoes respiration and carbon dioxide is evolved during respiration. So that process gives out carbon dioxide into the atmosphere. At the same time, during combustion also, there is carbon dioxide evolved into the atmosphere. So, in one way, we consume and use up carbon dioxide mainly by the process of photosynthesis, whereas carbon dioxide is being given back to the environment as well. So, if we discuss those. Now, this gas brought the temperature of the Earth's atmosphere to an optimal level for living organisms. This is also important, students. Now, you are familiar with the concept of greenhouse effect. I am sure you would have seen greenhouses where they grow plants. And the temperature inside the greenhouse is somewhat warm, even though the environment temperature is less. A similar thing happens around the Earth. Now, if we take the Earth has an atmosphere around it. Now, in this atmosphere, this is the atmosphere, there is 0.03% of carbon dioxide. Now, there are other gases also. Now, there is water vapor, there is methane, there is nitrous oxide. All these gases are known as greenhouse gases. Greenhouse gases. The reason is this. When energy from the sunlight comes and reaches the Earth's surface and it gets reflected back. So, from the sun, the light falls on the Earth crust and it gets reflected back. Now, if all the energy is reflected back, then of course the atmosphere will be very cold, and especially during night time when the sunlight is not falling on that part of the Earth. So, there what happens is, there are these gases, the greenhouse gases in this atmosphere. What they do is, they trap a part of this energy. The radiation from the sun is trapped by these greenhouse gases. So, here CO2 traps energy from sun. So, like CO2, all the greenhouse gases, they trap a part of the energy. So because of that, there is a certain temperature for the atmosphere. So that is why all the organisms are able to live properly. So carbon dioxide helps to maintain the temperature of the Earth's atmosphere. So that is very, very useful for us. So that is the first one. This gas brought the temperature of the Earth's atmosphere to an optimal level. Very important. It has to be an optimal level. When we say optimal level, not too high, not too low. Suitable for the life on Earth. Optimal level for living organisms. Then the next one. This is something I told you all before. It acts as a raw material for photosynthesis, the process that meets the food requirement of all living beings. So when we say photosynthesis, what is the process? Photosynthesis. You all are familiar with the reaction, how photosynthesis occurs. There are raw materials, carbon dioxide, water, in the presence of light energy, that is the sunlight or light energy, and there needs to be chlorophyll. Produces glucose and oxygen. So glucose is the main product, that is the food that will be converted to other forms, and all the organisms, all the other consumers depend on plants. Plants produce their own food by the process of photosynthesis. So here carbon dioxide, that is one of the raw materials. So that is very, very important to us. So what I have written down here is the word equation. You can give this as the balanced chemical equation also. So you are familiar with balanced chemical equation, students. If you are to write that, carbon dioxide plus water gives rise to glucose, C6H12O6 and oxygen gas. You need to balance this equation. Since there are 6 carbons in glucose, you need to have 6 carbon dioxide and again 12 hydrogens. To balance that, you need to have 6 water, and if you count the oxygens, 6 into 2, 12 plus 6 oxygen, 18 oxygen atoms. So there are only 6 oxygen atoms here. Because of that, you need to put a 6 there. So you get 12 more oxygen atoms. So that is the balanced chemical equation for the process of photosynthesis. But there also you need to write light and chlorophyll. We will be discussing the process of photosynthesis in your next grade in more detail. But since you are familiar with this, you have learned this process before also, you should be familiar with both the equations. And you have learned the balancing of equation in this lesson. So that is another process where carbon dioxide is important. So it helps to maintain the temperature, then it acts as the raw material for photosynthesis. And here, what I have already explained, carbon dioxide occurs in a percentage as small as 0.03% by volume. So if you take the atmospheric air, if you take 100 parts of the atmospheric air, 100 volume, then only 0.03% is carbon dioxide. So that is the introduction to carbon dioxide. With that, students, I will move on to the next slide where we will be discussing the chemical and physical properties of carbon dioxide. So, physical and chemical properties of carbon dioxide. Now, to understand that, what is the chemical formula? CO2. CO2. So, here carbon is 12 and there are 2 oxygen atoms. Relative atomic mass of oxygen is 16 into 2. So, you will get the value as 44. So if we calculate the relative molecular mass of carbon dioxide, it is 44. If you are to write the relative molecular mass, what do? You need to add up the atomic masses of the constituent elements. So there we found it as 44. There is no unit. What if we need to find the molar mass? You all know that. The same value with the unit grams per mole. And also, if you take the mass of unit volume of carbon dioxide, that is the density, that is greater than that of air. So, carbon dioxide is more denser than air. If we look at the properties, the density, carbon dioxide is more denser than air. CO2 is more denser than air. So that is the density of carbon dioxide. Then the relative molecular mass. Already I have calculated it for you all. It is 44. Relative molecular mass 44. Then combustion. You are familiar with this also. You would have seen carbon dioxide fire extinguishers. So what does that mean? It can put out fire. So if it can put out fire, that means it is not a supporter of combustion. It is a non-supporter of combustion. So you have to remember that when we say combustion, non-supporter of combustion. Non-supporter of combustion. So students, you all have to remember we have discussed two more gases before and this is the third gas. All of them have different properties when it comes to combustion. Hydrogen is a combustible gas that acts as a fuel, whereas oxygen is a requirement for combustion. It is a supporter of combustion. And carbon dioxide, it is a non-supporter of combustion. So when you discuss properties, students, it's better if you can compare with other gases, similar materials. So under this topic, we are discussing three gases. So there you need to compare the properties. It is better and it's easier. Then if you take the solubility, this is also slightly soluble in water. Slightly soluble in water. Slightly soluble in water. All the three gases are slightly soluble in water. So only a small amount dissolves in water. And also it is a colorless and odorless gas. So like all the other gases, nitrogen, hydrogen, oxygen, even carbon dioxide, all these are colorless and odorless gases. That is why although we have them in the atmosphere, we don't get any smell or we don't see any color unless the air is polluted. So that is the properties, those are the properties of carbon dioxide, both physical and chemical properties. I am sure you all can understand that. So we will move on to the next slide where we can discuss a reaction that can be used to produce carbon dioxide in the laboratory. So carbon dioxide gas can be prepared by reacting calcium carbonate with dilute hydrochloric acid. Usually carbonates with dilute hydrochloric acid or acids will give rise to carbon dioxide. That is like a common reaction. So here it is calcium carbonate with dilute hydrochloric acid. So you all know the formula of calcium carbonate, CaCO3 plus hydrochloric acid, HCl. When this reacts, you will get calcium chloride plus carbon dioxide plus water. Three products: calcium chloride, carbon dioxide and water. Check whether the equation is balanced. All the atoms are not balanced. Here you can see calcium, one calcium but there are 2 chlorine atoms. Here there is only 1 chlorine atom. The same way, if you look at hydrogen, 2 hydrogen atoms on the product side, only 1 hydrogen in the reactant side. So here it has to be 2 HCl. Then of course everything is balanced. Calcium carbonate plus 2 HCl gives rise to calcium chloride plus CO2 plus H2O, even oxygen. There are 3 oxygens here, 2 and 1, 3 oxygen atoms there. So that is the balanced chemical equation for the reaction of calcium carbonate with hydrochloric acid, that also dilute hydrochloric acid. So you will get carbon dioxide. Now in the lab, we have calcium carbonate that is there as calcium carbonate. You can get the calcium carbonate powder. But you can get this calcium carbonate from other substances also, even in the household. Now for example, if you take eggshells, eggshells have calcium carbonate. Then there are shells of some animals, the seashells. You're familiar with mollusks. Normally the exoskeleton, outer skeleton of the mollusk. If you take the snail, the shell of snails, that is also made up of calcium carbonate. So eggshells have calcium carbonate. Then even marble chips. Marble chips, those also contain calcium carbonate. Even shells of some organisms. You can say external shell of mollusks. That also contains calcium carbonate. So if you are doing this in the household, instead of calcium carbonate, you can take eggshells, or if you have marble chips, that can also be used. And if you find, if it is the only the shell of a mollusk that is remaining, you can use that also. Sometimes you come across pieces of these, the external shell of mollusk. So any of these can be used. And what is the other name given for calcium carbonate? It is also known as limestone. So calcium carbonate is also known as limestone. Then instead of hydrochloric acid, we can also use vinegar. Vinegar is acetic acid, CH3COOH. Now we have used vinegar before also to produce hydrogen. So that is an acid that is also somewhat dilute because we use that for cooking. So we can use vinegar. With eggshells, you can get carbon dioxide. Otherwise, if you don't have any of these, even baking powder, baking soda, that also can be used instead of calcium carbonate. Those are also carbonates. With vinegar, you will get the carbon dioxide gas. So for us, because we are doing it in the lab, we will be using this reaction where we use limestone or calcium carbonate and dilute hydrochloric acid. So these are things, students, that you need to remember. With that, I will move on to the next slide. So activity, collecting carbon dioxide gas in the laboratory. So we will see how we can collect the carbon dioxide in the lab, and also these are the materials that are needed. So required materials. First I'll label the materials on this side. So here you can see this is a conical flask. Conical flask. Then we will need test tubes. And we will need dry equal. Then on this side, we have the rubber stopper, or as I have told you all, we can also use the cork stopper. Usually we have the rubber stopper in the lab, but if we have the cork stopper, that also can be used. Then we need trough with water, and also we need a matchbox. Then we have the rest of the materials. Now you are familiar with this funnel. What is it? It is a thistle funnel. So here we need a thistle funnel. Thistle funnel. Then we need glass tubes. We need rubber tubes. Then here we have dilute hydrochloric acid. Dilute hydrochloric acid, dilute HCl. And you all know when it is in the solution form only, we call it hydrochloric acid. So there we have the calcium carbonate. So I will write the chemical formula, calcium carbonate, or you can say limestone, or else you can use these eggshells. And here we will need lime water. Lime water. When we say lime water, that is calcium hydroxide. Lime water is calcium hydroxide. So here students, a few things related to limestone. Now you have calcium carbonate, that is limestone. If you heat it, you can remember the decomposition reaction. It becomes calcium oxide evolving carbon dioxide gas. This is known as quicklime. And when that is dissolved in water, when you dissolve quicklime in water, you get calcium hydroxide. This is what we call as lime water. Or another name for lime water is slaked lime. Now this is a colorless solution. Calcium hydroxide or lime water or slaked lime is a colorless solution. Colorless solution. We will be using this to test and identify carbon dioxide. So in the previous procedures also students, you all can remember whenever we collect the gas, we do an activity to test and confirm that we have collected that particular gas. So here to confirm that we have collected carbon dioxide, we will be using lime water or slaked lime, or that is calcium hydroxide. So these are the materials that we need. Again, if we look at the materials, you can see here conical flask, we need a rubber stopper, then a thistle funnel, glass tubes, rubber tube, then we need test tubes, trough with water, dilute hydrochloric acid, so they are calcium carbonate or limestone or eggshells, then dry equal, matchbox, lime water, that is calcium hydroxide. So these are the required materials. So in the next slide with the diagram, I will explain how we put up how we get all these things arranged into the apparatus that is needed to collect carbon dioxide gas. So here the method, so you can see the diagram here students. I will label the parts on the other side first. So here you can see, you're familiar with this, the thistle funnel. Thistle funnel. Then what is this? We have the glass tube and usually the rubber tube is connected to it. It is the delivery tube. Delivery tube will have both glass tube and rubber tube connected. So that's going to be the delivery tube. Then we are planning to collect carbon dioxide. So That is going to be carbon dioxide gas. Carbon dioxide gas. You're familiar with this. This is the gas jar. And here we have the trough. And there is the beehive shelf. And we need to have water. So again students, with the materials needed, we need to have the gas jar and also the beehive shelf. Like in the previous activities, I explained the use of both beehive shelf and the gas jar. I will go back to the previous slide. Here we don't have the gas jar and the beehive shelf. I will include that as well. So we need to have the gas jar and the beehive shelf. So we need a gas jar and the beehive shelf. Two more materials that are needed. So if we are collecting the gas into the test tube, we don't need the gas jar or the beehive shelf. But if we are using the setup shown in the diagram, we need those two materials. So again, I will go back to the next slide. Here, if we label the rest of the parts, this is the stopper. So we have the stopper there. And here this is the conical flask. Then we have the dilute hydrochloric acid. And here we have calcium carbonate. So I will label this as calcium carbonate, but depending on what we use. We can use limestone, we can use eggshells or even marble chips. All those are calcium carbonate. So accordingly you can label it. Then if we look at the setup properly. So you need to have the conical flask first, a clean one. Into that we need to take the calcium carbonate, the required amount of calcium carbonate. Then you need to connect the thistle funnel. And how do you connect it? You have to make sure that the thistle funnel comes right up to this calcium carbonate. It has to be very close to that. So that when we add the acid, now through this only we add dilute HCl. So when the acid comes in, it will come in contact directly with the calcium carbonate. And also we can avoid splashing of acid and the acid will not enter into the delivery tube. So it will come and fall at the bottom of the conical flask. So we avoid splashing and the acid entering into this delivery tube as well. So then it is important, you have to remember that also the delivery tube has to be above this acid solution. The reactants are here, the delivery tube has to be somewhat above that. Why is that? Here also students, now when we discussed carbon dioxide is more denser than air. But still, when there is a reaction taking place, always the gases that are produced, they are liberated, they usually come up. So therefore, the carbon dioxide comes up, it will enter into the delivery tube, it will go out through the delivery tube. So here we will have the glass tube, then it's going to be the rubber tube connected there. You can see that when I do the activity in the lab. So there it will be the rubber tube. And we have to make sure that a lot of gas does not escape from the sides between the cork and the conical flask. So it has to fit properly. But still there is an opening here. Even if a small amount goes out, that is not going to be a huge problem. Because here we need to collect the gas. We are not measuring anything. So when the reaction occurs, calcium carbonate reacts with dilute hydrochloric acid, carbon dioxide is liberated, that will enter into the delivery tube, come through the rubber tube. Then here we have the trough containing water. On that we place the beehive shelf. And I have explained this to you all before also. If you look at the beehive shell, it is a structure like this. It has a circular shape. There is an opening here, and this is like a small stage, this circle, and it's about this much in height. And on the side also there is an opening like that. So we keep the beehive shelf in such a way that you can send this rubber tube through this opening, so that it is easy to direct the gas into the gas jar. Now, before we place the gas jar, what should we do? We have to fill it completely with water, so that there is no air, no other substances are there inside the gas jar. We have to completely fill it with water. We can do it inside the trough, or we can fill it with water, cover it with a piece of glass, invert it and bring it to this point, and then place it on the beehive shell. I explained this before also, students. If we don't have the beehive shell, we will have the rubber tube and we will have to place the gas jar on top of it, or else we have to be holding it. Then of course, it might be difficult for the gas to enter into the gas jar. So the advantage of having the beehive shelf is to easily allow the gas to flow into the gas jar. So then what happens? Like shown in the diagram, now carbon dioxide is slightly soluble in water, but the amount that dissolves in water can be neglected. It won't cause a problem when we collect carbon dioxide. So only a small amount dissolves, but if you compare the densities, density of carbon dioxide is less than that of water. So because of that, carbon dioxide will go up, will get collected above water, and water will be pushed down. So water will be displaced downwards. So what do we call this process? It is known as the downward displacement of water. So by doing this, using this setup, this apparatus to collect carbon dioxide gas, we collect it by the method of downward displacement of water. So as I did before, students, we need to remember a few points. Most of them I have explained with the previous two activities, but the same things apply here also. So I will note down those points first. So when you consider preparing this setup, you have to remember the first one, thistle funnel has to be connected in a way that it comes down closer to the bottom of the conical flask, or we can say closer to the calcium carbonate. That is one. Then the next one, delivery tube is connected away from the reactants in the conical flask. So then what happens? When calcium carbonate and dilute hydrochloric acid react, carbon dioxide is formed. It is taken through the delivery tube, into the gas jar. It is collected inside the gas jar. So how do we place the gas jar? It has to be completely filled with water. So then gas jar should be completely filled with water and inverted in the sense turned upside down, turned upside down and placed on the beehive shelf without trapping any air bubbles. Then only we will be collecting only carbon dioxide gas. There will be no other gases. Then what is the next one? Beehive shelf. Beehive shelf helps to direct the CO2 gas from the delivery tube into the gas jar. And what is this method called? This method of collecting CO2 gas is known as downward displacement of water. And how is that possible? Because CO2 is less denser than water. So we have been using the same method, downward displacement of water for all the gases. Why? Because all three gases, they are less denser than water. That is why they go up and push the water down and get collected above the surface of water. So water is displaced downwards, downward displacement of water. Is that clear to you all? Then as I told you before, we will be using lime water, colorless solution of lime water, that is calcium hydroxide, is used to identify carbon dioxide gas. But in addition to that, you can remember students, with the materials we had the dry ether, because for the previous two gases, both hydrogen and oxygen, we use the splinter. For hydrogen we use the burning splinter, for oxygen we use the glowing splinter. So just to confirm that it is not those two gases, we will be using the splinter as well. And also you know the property. Now carbon dioxide is a non-supporter of combustion. So what should happen? We use it as a fire extinguisher as well. So if you introduce a burning splinter, then the fire has to be blown off. It should go off because it is a non-supporter of combustion. So, we will be doing that as well. So, these are the materials and this is how we need to have the setup. So, these are the things, students. If you are given a diagram, you should be able to identify and label all the materials given there. The conical flask, calcium carbonate, then you have the dilute hydrochloric acid pass through the thistle funnel, the stopper, delivery tube, trough with water, beehive shelf, and you have the gas jar into which we collect the gas by the downward displacement of water. So, that is the apparatus. I will move on to the next slide now where I go through the procedure again and then we will do the activity in the lab. So, this is the method. Set the apparatus given in figure and fill some test tubes with carbon dioxide. So, I told you all this before also, student. We need to fill some test tubes with carbon dioxide. Before also when we did the activity, you can remember I used the gas jar to show you all the proper downward displacement of water. Then we can use to fill some test tubes that also filled with water with downward displacement of water. So, it is easy to take out the test tubes and do the relevant test. So, we do that. Then, like I told you all, light a dry ether and introduce it with the flame. This is important. You need to introduce it with the flame into the test tube containing carbon dioxide gas. So, this is to test whether it is a supporter or non-supporter of combustion. So, you all know carbon dioxide is a non-supporter of combustion. To test that only we do this procedure. Then we have the next one. Dissolve a little slaked lime. Now, I told you all this. You can take the quick lime and dissolve it in water, or if you have calcium hydroxide itself, that is slaked lime. This is slaked lime in the solid form. Solid. You can take that and dissolve it in water in about 50 milliliters of water carefully and filter through a filter paper because we need to have a clear solution. If you dissolve slaked lime, the solubility is somewhat less. So, because of that, there can be a little amount of the solid remaining. So, we need to filter it and we need to get the clear solution. Add about 5 milliliters of this solution to a test tube containing carbon dioxide. Stopper the tube tightly and shake well. So, you can do it that way. Add the same volume of lime water to a test tube with normal air, stopper and shake well. Compare the colors of the solutions in the two test tubes. So, we can do this activity again in two different ways, students. One thing, you can take two test tubes like mentioned in the activity. So, into one, we can have CO2. In the other one, we can have air. To both the test tubes, we can take calcium hydroxide and we can use the stopper and we can shake them properly and observe whether there is color change taking place. This is one way of testing how the change occurs with carbon dioxide. Otherwise, what we can do is, so here we have the conical flask with calcium carbonate and hydrochloric acid with the stopper from the delivery tube. What we can do is, we can bubble it or send it into calcium hydroxide, that is lime water. So, you can pass a little bit of carbon dioxide as it is being produced into this test tube containing calcium hydroxide or lime water, then you can observe the color change also. So this is to compare and understand how or what happens when you mix carbon dioxide with lime water and when you try to react or mix air with lime water. You can do this or else we can do this procedure. This is again a test to identify and confirm that it is carbon dioxide. So that is the procedure. And here you have to remember, students, the slake lime that we are taking or the lime water that we are taking, it has to be a clear solution. So then only you will be able to see the color change. There should be no solid components. It has to be a clear colorless solution. I am sure you all can understand this procedure. So now let's go to the lab and do the activity. Okay, students. So now we are going to see how we can collect carbon dioxide gas in the laboratory and also how we can confirm that it is carbon dioxide gas. So you're familiar with all these materials. Here you can see this is hydrochloric acid, one of the chemicals that we need. And here you can see this is limestone. Limestone is calcium carbonate. So it is a white color solid substance. You can see that we will be using hydrochloric acid, dilute hydrochloric acid and calcium carbonate. So that reaction will give rise to carbon dioxide. And here I have the conical flask. I have clamped it so that it is easy to handle the conical flask when I fill in the hydrochloric acid and carry out the reaction. So then we have this one. This is the thistle funnel. So you all know, you can see here, students, the thistle funnel has to be long. And this is the glass tube with the rubber tube connected to it. That is what we call as the delivery tube. And you have to notice that the levels of the delivery tube or the glass tube and the thistle funnel have to be like this. Thistle funnel has to be long, so it comes up to this point, whereas the delivery tube has to be higher above, so that the gas that is evolved during the reaction will go through that and get collected into the gas jar. So we will be connecting it like that. And here I have the trough with water, and then you all are familiar with the gas jar. We will be filling water into this without trapping any air bubbles or any other gas bubbles. We will have to invert it with water. So to do that, I have the piece of glass here. So with this we can fill water completely, then cover it, invert it, and we can place it easily on the beehive shelf. So you know what the beehive shelf is. This is the beehive shelf, students. Here you can see there is an opening here and there is an opening on this side as well. So we send the delivery tube through this opening so that it can be held in place easily. I explained this to you all before also. And through this opening, the gas will rise up, displacing the water inside the gas jar. So that is how we are going to collect the carbon dioxide gas. Then you can see here we have calcium hydroxide, that is lime water. Can you all see the color? Now it's a clear solution, almost a clear solution, but with time it can quickly react with carbon dioxide in air and it will become milky in color, slightly milky in color. But when we pass carbon dioxide into it, you can see it becoming milkier. So from that you can understand or confirm that the gas collected is carbon dioxide. Then I have the test tubes into which also I'll be collecting carbon dioxide gas to carry out the test for carbon dioxide. Then again, to confirm how it reacts or how it acts with the combustion process, whether it supports combustion or does not support combustion, we will be using this splinter. So we will be using a burning splinter there. So now that you are familiar with all the glasswares, I will start the procedure. We need to take calcium carbonate, limestone, into the conical flask. Then I will connecting this here. Now that I have connected the thistle funnel and the delivery tube, now we will need to fill the gas jar with water. It has to be completely filled so that there are no gas bubbles or air bubbles trapped inside it. So as I told you all students, either we can fill water to this, cover it with this glass and then invert it in, or else we can directly do it inside the trough itself. So I can fill it within the trough that has water, but have to make sure that there are no gas bubbles, and then we can invert it, and you have to check whether there are gas bubbles or not. Then what we need to do is we need to place the beehive shelf inside, and on that we have to place the gas jar containing water. Okay, so then it is I will turn it to this side so that I can insert the delivery tube easily in here. So now the gas will get collected inside the gas jar. So we need to add the dilute hydrochloric acid. We need to pass it through the thistle funnel. So here students, you all can see the reaction occurring inside the conical flask. So then with time, you will see how the gas gets collected. So now here students, you all can see the reaction taking place. So then the gas will be delivered into the gas jar. It will be transferred into the gas jar. In a while, you can see the gas being collected. Here you all can see students the gas bubbles coming up, and you can observe the displacement of water. It's flowing downwards and the gas is collecting over the water surface. You all know the reason. Carbon dioxide is less denser than water. So it goes above water and water gets displaced down. So we call this the downward displacement of water. So here when calcium carbonate reacts with dilute hydrochloric acid, carbon dioxide is evolved and that is collected by the method of downward displacement of water. So you can see the gas bubbles going up and the carbon dioxide getting collected over there. And you all know carbon dioxide is slightly soluble in water, but that is not a problem here. Even though a small amount dissolves, still there will be the carbon dioxide gas collected. So we will wait till we get some more carbon dioxide gas. When we shake the conical flask, the reaction occurs a little bit more. So you can see the gas evolving. So this is the method in which we collect carbon dioxide gas. So here this is the method of downward displacement. Then you all know students, we need to identify that this is carbon dioxide gas. To do that, we do two tests, one with the burning splinter, the other one with calcium hydroxide, that is lime water. So for that reaction, I will be using a test tube. Now you all know, in addition to the downward displacement of water, carbon dioxide is more denser than air. So what will happen if you pass carbon dioxide into a test tube containing air? Air will be displaced upwards and the carbon dioxide will get collected below the air. So that is what I am going to do now, and then I will test it with a burning splinter to see whether it supports or does not support combustion. So I will remove the tube there, and if I insert it right down to the bottom, you can observe the reaction happening here. But the thing is, like the downward displacement of water, we cannot see the air being displaced because both air and carbon dioxide both are colorless gases. So, but we will have to wait until it gets collected for some time. So, carbon dioxide will go down, the air will be displaced up. So, here students, you all can see the reaction taking place and the carbon dioxide will be collected inside this test tube by the method of upward displacement of air. So, as I explained to you all, air will be pushed up, carbon dioxide will get collected at the bottom because carbon dioxide is heavier than air or more denser than air. So, I think that should be enough. So, I will just cover it with my finger. I need a burning splinter. So when I insert the burning splinter, you can see it just goes off. The reason is carbon dioxide does not support combustion. It is a non-supporter of combustion. So then we will have to collect some more carbon dioxide into this as well. The same method, upward displacement of air, and then we will add lime water into it as well as a lime water into a test tube containing air. So there is air inside this and I'll be collecting carbon dioxide into this. Okay. So I will insert the tube here. So here again students, you can see the reaction. So the carbon dioxide will get collected into this. And once I hold it for some time, I will cover it with a rubber stopper. So now I'm going to cover it with a rubber stopper. So in this I have carbon dioxide gas, in the other one I have air. So then I will add a small amount of lime water into the test tube containing air. And into the test tube containing carbon dioxide. So here when we shake both the tubes. Now you all can see here students. Immediately you can observe the color change. Can you all see the difference? This is air and lime water. This is carbon dioxide and lime water. So that is one way to confirm that when we bubble carbon dioxide into lime water, it becomes milkier. Compared to air, this is more milkier. And then you all know students, if we bubble carbon dioxide continuously into lime water, what happens there? Initially, with carbon dioxide and lime water, there is the formation of calcium carbonate. So that does not dissolve in water. That is why we get this milky color. But if we keep on passing carbon dioxide further, then you will see the color will disappear. It will become clear again. The reason is the carbon dioxide will react with calcium carbonate and water, forming calcium bicarbonate. That is more soluble in water. Because of that, the milky color or milkiness will disappear. So here you can see the milky color. Now we will pass more carbon dioxide. So now I am going to bubble carbon dioxide into this. So for that I will need to insert the rubber tube so that it gets bubbled here. I will need to add some more HCl so that the reaction will occur. So here you can see still the color of course is increasing. You can see, students, there are gas bubbles evolving. Observe the color. Now can you all see the change? So here you can see, students, with time the color has decreased now. Okay, students. So you all were able to observe how I collected the carbon dioxide gas with the reaction of hydrochloric acid and calcium carbonate. So the process was the downward displacement of water. For that we used the gas jar. Then into a test tube I collected carbon dioxide using the upward displacement of air. And when we tested with a burning splinter, you saw it burns off. The reason is the flame is put off immediately. The reason is carbon dioxide is a non-supporter of combustion. Then after that, we compared two test tubes containing one containing air and the other one with carbon dioxide. We tested with lime water, that is calcium hydroxide. With air, there is no color change, but with carbon dioxide, lime water becomes milkier. But then when you continuously pass carbon dioxide into it, the milky color becomes colorless again, or the milky color disappears. So now you all know the reason. When we bubble carbon dioxide into calcium hydroxide, there is calcium carbonate formed that does not dissolve in water. Because of that, we get the milky color. But when you continuously pass carbon dioxide, there is calcium bicarbonate formed that dissolves in water. Therefore, the milky color disappears. So we can confirm that the gas we collected by this activity or during this activity is carbon dioxide. Okay, students. So did you all observe the activity clearly? Were you all able to see how the downward displacement of water takes place and how the carbon dioxide gas is collected over water? I am sure you all did. And also you were able to see when I inserted the burning splinter. It does not burn continuously. Why? Because carbon dioxide puts off the flame. It stops the combustion process. So from that we can confirm that it is a non-supporter of combustion. Then what else did we do? I used the test tube containing lime water. Into that, when we bubble carbon dioxide, what did you all see? You saw the solution becoming milky in color. Then what happened if I bubbled continuously for more time? What happened to the color? You were able to see that the color disappears. So initially when we pass carbon dioxide into lime water or slake lime, that is a colorless solution, it becomes milky in color. But when you keep on sending carbon dioxide into that, or passing or bubbling, you can use any term. When you bubble more carbon dioxide into that, you can see the color disappear. It becomes clear again. We will understand that in the next slide, but for now, I will write down the observations and the conclusions. So here we can say, when calcium carbonate reacts with dilute HCl, carbon dioxide is liberated. This is collected by the downward displacement of of water. Then burning splinter is blown off when exposed to carbon dioxide. Lime water becomes milky when carbon dioxide is passed into it. Later becomes colorless. And also students, like it was explained in the procedure, if you take 2 test tubes, into one if you have carbon dioxide and inside the other one if you have air, and if you add a small amount of lime water into that and you shake it well, what will happen? The test tube containing carbon dioxide, the lime water will turn milky. Whereas the lime water inside the test tube containing air, it will not become that milky. Why? Because even if it slightly changes color, there is only 0.03% of carbon dioxide in air. So that's a very, very small amount. But if you keep it exposed to air for a long time, then of course the clear lime water can become milky. Why? CO2 is soluble in water, so little by little with time it can dissolve in the lime water solution and that can become milky in color. But normally when we do it quickly in the lab, you will not see a color change with air, but you will see a color change with carbon dioxide. So from all these observations, we can come to the following conclusions. We can say carbon dioxide is collected by the downward displacement of water. Then with the burning splinter, it is blown off. What can we say? It is a non-supporter of combustion. CO2 is a non-supporter of combustion. And we can say we confirmed the gas collected is carbon dioxide by testing with lime water. Testing with lime water. So that is like a test to identify that the gas evolved or gas liberated during the activity is carbon dioxide. So those are the observations and conclusions. You can see here students the observation when calcium carbonate reacts with dilute hydrochloric acid, carbon dioxide is liberated. This is collected by the downward displacement of water. Then burning splinter is blown off when exposed to carbon dioxide. Lime water becomes milky when carbon dioxide is passed into it, later becomes colorless. I told you all I will explain that reaction in the next slide. And from those, we were able to come to these conclusions. Carbon dioxide is collected by the downward displacement of water. Then carbon dioxide is a non-supporter of combustion. And from this observation, initially the calcium hydroxide becoming milky, and later when more carbon dioxide is bubbled into it, it becomes colorless. So from that, we can confirm that the gas collected is CO2 by testing with lime water. So those are the conclusions that we get from this activity. So I am sure students, you all were able to observe the apparatus clearly and you saw all the observations. So you have a very good understanding about this activity and how to collect carbon dioxide and to identify that it is carbon dioxide. Okay students, so these are the observations and conclusions of the activity. With that, I will move on to the next slide. For your attention, though a little amount of carbon dioxide dissolves in water when it is collected over water, it is not a barrier to collect samples of the gas. So that is why it is possible to use downward displacement of water. Downward displacement of water. So before I explain the activity with lime water, this is something that you need to remember students when we will be discussing the uses of carbon dioxide. You know that carbon dioxide is used to make fizzy drinks. That is possible because carbon dioxide dissolves in water. That is why it gives a sweet taste for all these fizzy drinks. So that does not become a problem here. It is not a barrier in order to collect samples of carbon dioxide using downward displacement of water. That is something you have to keep in mind, students. So with that, I will move on to the next slide. Okay. So here you can remember students, I have already explained to you all the method that we use to collect carbon dioxide gas. That is the downward displacement of water. So here also the method used to collect the gas is the downward displacement of water. What is the reason? Density of carbon dioxide is less than the density of water. So here you can see, but as the density of carbon dioxide is greater than that of normal air, it can also be collected as shown in figure. So we are able to use, you have to be careful students, we are able to use downward displacement of water because water is more denser than carbon dioxide. That you have to remember. That's why carbon dioxide goes up and water is pushed down. It is displaced downwards. But here, we consider the density of carbon dioxide is greater than that of normal air. So when you consider air, carbon dioxide and water, air is less dense, whereas carbon dioxide is more denser, water is even more denser. So this is how the density is. You have to remember that. Water is more denser, so it is displaced downwards. But air is less denser, or carbon dioxide is more denser than normal air. So what we can do is we can use another method where we displace the air upwards. Because air is less dense, carbon dioxide is more denser. So for that only, we use this particular setup. Here you can see, you can pass the carbon dioxide gas through the delivery tube into a gas jar containing air. And this air will be pushed upwards. Air will be displaced upwards. And the carbon dioxide will get collected at the bottom. Why? Carbon dioxide is more denser, air is less denser. As we pass carbon dioxide, that will go down and displace the air up. You can remember that. So this method of collecting carbon dioxide is known as upward displacement of air. So that is the explanation given here. Since the density of carbon dioxide gas coming from the delivery tube is high, it reaches the bottom of the jar. So what I explained, it goes to the bottom of the jar. When the gas fills the jar, air inside is displaced upwards. Very important. Air inside is displaced upwards. You have to remember this. Therefore, this method of collecting a gas is known as upward displacement of air. You have to remember that, students. Upward displacement of air. So, in all the three activities, you have to recall what we discussed previously. We use the method of downward displacement of water. If we take all the gases, hydrogen, oxygen and carbon dioxide, they are all less denser than water. You have to remember that. Density of water is higher than all these gases. So that is why we were able to collect them using the downward displacement of water. But you have to remember, students, we discussed with hydrogen also. Again, you have to compare. Then you can remember easily. Hydrogen is lighter than air. So you can remember we collect hydrogen gas by the downward displacement of air. But here, this is carbon dioxide gas. This is more denser than air. So what we do is we collect it using upward displacement of air. So you have to be clear with that. I'm sure you all can understand that. So with that, I will move on to the next slide. I told you all before when we did the activity that I will explain how we use lime water, that is calcium hydroxide, to identify that the gas collected is carbon dioxide. So you can remember initially when we bubble or pass carbon dioxide into clear lime water solution, what happens? It becomes milky in color. Thereafter, when you keep on passing carbon dioxide, the color disappears. The reason, that is what we are going to discuss now. So, the test for carbon dioxide with lime water. What is lime water? Calcium hydroxide solution. That is what we call as lime water. You have to remember the chemical formula also. So, you will see that lime water turns milkier when you pass carbon dioxide into it. So, lime water turns milkier when you pass carbon dioxide into it. I told you all, students, if you have lime water exposed to air, even the carbon dioxide that is present in air can dissolve in lime water. So, although we want it to be clear and colorless, it can be slightly milky, very slightly milky, because there's only a small amount of CO2 in air. But when you pass, when you send or pass or bubble carbon dioxide into lime water, it will become milky. This is the reason. Now here you have lime water. This is calcium hydroxide. Usually clear solution or slightly milky. To this we pass carbon dioxide. Then what happens is this calcium hydroxide reacts with this carbon dioxide and forms calcium carbonate plus water. Now this calcium hydroxide is somewhat soluble in water, but calcium carbonate is, you can say, insoluble in water. That is why you get this milky color. There is water, this is not soluble, so you get a milky color solution. But what happens is, when you keep on passing, when you pass more CO2 into the milky solution. What happens is you have calcium carbonate, you have water, and with that you are adding more CO2. Then what will happen is all of them react together and form calcium bicarbonate. This is calcium bicarbonate. Calcium bicarbonate. So this calcium bicarbonate is soluble in water. This is soluble in water. Therefore, milky color disappear. So that is what happens there. Initially you have calcium hydroxide solution. You pass carbon dioxide, it forms calcium carbonate. That is less soluble in water, so you get the milky color. Then if you continuously pass carbon dioxide, all of them react and form calcium bicarbonate. That is CaHCO3 twice. This calcium bicarbonate is soluble in water. Because of that, the milky color disappears. You have to remember this. And this is the test for carbon dioxide. So this is the observation that we get. You will see that the lime water turns milkier when you pass carbon dioxide into it. But if more carbon dioxide is passed into the test tube containing the milky solution, then the milkiness disappears. Very important. Into the milky solution, then the milkiness disappears. So both these observations are used to confirm the presence of carbon dioxide gas. Or the gas that we collect is carbon dioxide is confirmed by this particular observation. I'm sure you all can understand that. And also students, you have to remember the compounds that are responsible for the milky color and the disappearance of the milky color. So with that, I will move on to the next slide. When carbon dioxide is cooled strongly under high pressure, the gas solidifies. You have to remember that. So we have the CO2 gas. On cooling, what happens is it becomes CO2 solid. Without becoming the liquid, it can become the solid. It solidifies. So the gas solidifies. The same way, when you heat carbon dioxide solid, it does not become the liquid. Instead, it directly becomes the gas. Now, water is different, students. You have the water vapor. When you condense the water vapor, what happens? It becomes liquid water. Then if you cool the liquid water only, it becomes ice. So there the physical state changes from gas to liquid and liquid to solid. The same way, if you heat ice or if you take ice and place it in the environment, due to the environmental temperature, the ice will melt and form liquid water. So again there, solid becomes liquid, and then if you heat water only, it will become steam. So their liquid will go to the gaseous state. But for carbon dioxide, you have to remember when you cool it, it goes from carbon dioxide gas to solid. The same way if we heat it. If we do the opposite, if you heat it, carbon dioxide solid will become carbon dioxide gas. So then, that is the reason why we use it as dry ice. When heated, the solid carbon dioxide directly turns into the gas without liquefying. That is what I have explained there. This is important. without liquefying, it turns into the gas. So it does not become a liquid like ice. So like I told you, ice becomes water, then only becomes water vapor. But here that does not happen. Directly from the solid state, you get the gaseous carbon dioxide. Therefore, solid carbon dioxide is known as dry ice. So you can see this picture, students. Now this is dry ice, what you see here. And here you can see when it vaporizes, when it is exposed to heat, the dry ice becomes gas. Carbon dioxide gas. So from solid, you get the gas. Is that clear to you all? So because of this dry ice has a lot of applications. Since the temperature of dry ice is minus 77 degrees Celsius, is very much lower than that of ice. Normally ice below 0 degrees Celsius. But here this is minus 77 degrees Celsius. So it is used as a supercoolant. Because the temperature is very, very low, we use it as a supercoolant, not a coolant, supercoolant. Now, normally when we say coolant, coolants are used in certain processes where you need to cool substances, keep them under low temperature. But here, carbon dioxide can be used as a supercoolant, very low temperature. And also the dry ice, that is what we use as supercoolant. And also that directly can be used to make artificial rain or artificial snow. So dry ice is largely used in food preservation. So if you want to keep something at a very low temperature, maybe fish, meat, so for that we can use it as a supercoolant to preserve it for a longer period of time at a very low temperature. And also it is used to create artificial rain. So directly the dry ice, it can be artificial rain or artificial snow. So because from the gaseous state it goes to the solid state and it has a very low temperature. It's used to preserve food as well as to make artificial rain. So that is again a use of carbon dioxide because it gets converted directly from the gaseous state to the solid state. And the solid state has a very low temperature. You all have to keep that in mind, students. Is that clear to you all? So with that, we will move on to the next slide. Here we discuss the uses of carbon dioxide. So most of these I have already discussed with you all. We discussed some of the importance. You have to remember that as well. Maintaining the temperature of the Earth atmosphere, being used as a raw material for photosynthesis. So those two are very, very important uses of carbon dioxide, but those are natural processes. Here we are going to look at uses of carbon dioxide where we use carbon dioxide to make other substances. So you're familiar with the first picture, the carbon dioxide fire extinguisher. We discussed that property also. When you insert a burning splinter, the flame is put off, the flame is blown off. Why? Because carbon dioxide is a non-supporter of combustion. So since carbon dioxide is a non-supporter of combustion, it is used in extinguishing fires. This is also something that you all already know, students. There are different grades of fire. Some fire can be put off with water. But if there is a fire related to electricity or fuel, like petrol, diesel, usually they are less denser than water. So what happens if you use water fire extinguisher? The oil comes over water and it burns further. So there we will have to use alternate methods. So for fire that is caused to electric circuits or fire where it is related to a fuel, we can use carbon dioxide fire extinguisher. So that is because it is a non-supporter of combustion. Then, since carbonic acid formed when carbon dioxide dissolves in water gives a taste it is used in the production of soda water and fizzy drinks. So, to produce soda water and fizzy drinks. Like this, you would have seen all the fizzy drinks. How is that possible? Because when carbon dioxide dissolves in water, it forms carbonic acid. This is carbonic acid. Carbonic acid. H2CO3 is carbonic acid. So, under high pressure, when they dissolve carbon dioxide in water, it forms carbonic acid. That has that sweet taste. But when you open the bottle, when the pressure is released, usually the carbon dioxide comes out. It decomposes actually. H2CO3 again becomes water and carbon dioxide. So that's why you see the bubbling nature like the foam here as it's shown here. The carbon dioxide is released, then eventually you end up with water. That is why after you open the fizzy drinks, usually if you leave it out for some time and then you try to drink it, you don't get that sweet taste and also the fizziness is not there because CO2 evolves very quickly. So, carbon dioxide, water gives rise to carbonic acid. You have to remember that. Then we have the next one that is also something that is already familiar to you all, carbon monoxide. Gas, the reductant essential for extraction of iron. You all know the meaning of reductant, or I use the term reducing agent when I discuss the extraction of iron using blast furnace, that method. So, there we use carbon monoxide gas as the reductant essential for extraction of iron is produced by reacting carbon dioxide with coke. You can remember this reaction, students. What did we do? In the blast furnace, you have coke. You all know this coke is different from that coke. That is a fizzy drink. This is carbon. Carbon is coke. So, what happens? You have carbon. It reacts with oxygen, forming carbon dioxide. Then this carbon dioxide further reacts with carbon and forms carbon monoxide. So, this is the reducing agent. Or reductant. That is used to reduce iron from the iron ore. You can remember that also. I am recalling what we have already discussed. You have hematite Fe2O3 plus carbon monoxide. We get iron plus CO2. So, here if we balance it, this is going to be the balanced reaction. So, carbon reacts with oxygen forming carbon dioxide and that carbon dioxide reacts with carbon giving rise to carbon monoxide. That is the reducing agent that reduces iron from its ore. So, since you have learnt all these reactions, you need to remember the balanced chemical equations as well. So, those are the uses of carbon dioxide. So, as a fire extinguisher because it is a non-supporter of combustion. Then, when it dissolves in water, it forms carbonic acid which has a sweet taste. So, therefore, it's used in fizzy drinks as well as soda water. And then, carbon monoxide gas that is produced from reacting carbon coke with carbon dioxide is used as the reducing agent in the extraction of iron. So, these are all important things that you need to remember, students. So, with this, I have come to the end of discussion on properties, then the collection of carbon dioxide gas and the uses of carbon dioxide gas. And also, I have come to almost the end of the lesson. So, with that, I will move on to the next slide. So, here an extra knowledge is given to you, students. You can see when writing a balanced chemical equation. Now, we are familiar with that, writing balanced chemical equations. The physical states are related to the reaction are often indicated in front of each reactant and product. It is not the front, it is at the back or after the reactant or product is written. So, not in front. As you can see here, students, we use one letter or two letters to denote the physical state. You are familiar with the physical state, solid, liquid and gas. So, for solid, we use S, liquid L, all simple letters, not capital letters, that is important, and gas G. But if it is a solution where the solvent is water, solution made with water, we call it an aqueous solution. So, for aqueous solution, we use AQ. That is very important. And if you look at the example, you can see this is a mistake in the book. So, you can see here, if it is a reaction between magnesium and oxygen, magnesium is in the solid state. So, after the reactant, not in front but at the back, after the reactant within brackets, you have to write the state. So, 2 magnesium solid with oxygen gas gives rise to 2 magnesium oxide, again solid. You have observed this reaction. When we burn a strip of magnesium in air using the Bunsen burner, you have seen it burning with a bright white flame and we get a white color powder or residue remaining. That is magnesium oxide. So, you can remember that, students. So, as an example, if we write another reaction, consider the reaction of sodium with water, sodium solid. Water is a liquid. You get sodium hydroxide, that is aqueous, and H2 gas. So, here sodium solid, water liquid, sodium hydroxide aqueous, because water is the pure liquid form. So, we say the state as liquid. But sodium hydroxide is a solid that dissolves immediately in water and forms the solution. So, you have to write it as aqueous, AQ. And hydrogen gas is evolved during the reaction. You can remember this reaction also. So, here in this, all 4 physical states are there: solid, liquid, gas and aqueous state. And also, students, you have to remember in the earlier method, we used to write this as a subscript. But now we write it in the same line. The same way we write the other letters, we write it in the same line and it has to be all simple letters. So, that is a way of denoting the physical states when we write the balanced chemical equation. So, here we need to have the balanced chemical equation. Can you all check? Now, we have 2 hydrogen gas but we have H here. So, what do we need to do? We need to have a 2 there. So, we need to put a 2 in front also so that we can balance it. Because of that, we will have a 2 here. 2 sodium reacts with 2 water, giving rise to 2 NaOH aqueous and 1 hydrogen gas. So, that is the balanced chemical equation with all the physical states included. Is that clear, students? So, with that, I will move on to the next slide. Then, we have come to the summary of the lesson. Summary: the changes taking place in matter can be classified as physical changes and chemical changes. So, we saw how we can identify physical changes and chemical changes. Physical changes can be reversed. So, if a solid becomes a liquid, the liquid can again become a solid. You can remember naphthalene. Whereas during chemical changes, the reactants are converted to products. So, from the existing substances, some other substances are formed. So, that is the chemical change. The change that involves only the change in physical state of a substance without changing its composition, such as melting of a solid, vaporization of a liquid, condensation and solidification of a gas, following cooling and freezing of a liquid are all physical changes. So, different changes: melting. Ice melts and forms water. Then vaporization, water vaporizes into vapor or steam. Then condensation. What is condensation? Steam or water vapor from the atmosphere condenses and form water. Solidification, like we discussed before, a liquid becoming the solid. When we say solidification of a gas, you all can remember the example. Carbon dioxide gas becoming dry ice, carbon dioxide solid. Following cooling and freezing of a liquid, that is water becoming ice. Freezing of a liquid, an example is water becoming ice. So, these are all physical changes and you are familiar with all those changes. The change that bring about the formation of a new substances from the existing substances are known as chemical changes. So, that is what I said, from the existing substances, those are the reactants, we get the new substances, products. Chemical reactions are of 4 types. You are familiar with that. Combination, we call it as chemical combination reaction. Then chemical decomposition or simply known as decomposition. Then we have the single displacement and the double displacement reaction. So, you all are able to identify all these reactions. Chemical changes can be represented by a balanced chemical equation. So, it has to be either a chemical change can be represented by a balanced chemical equation or chemical changes can be represented by a balanced chemical equation. Symbols of elements and formulae of compounds. So, for elements we call it symbols. For compounds we say that is the chemical formula, many chemical formulae. So, symbols of elements and formulae of compounds that take part in a chemical reaction are used to write the balanced chemical equation. We have done that, we have practiced that. So, you are familiar with balancing chemical equations. A lot of information can be drawn from the correctly written chemical equations. You can remember we use the reaction between hematite and oxygen, the balanced chemical equation, to get a lot of information from that. So, with that I will move on to the next part of the summary. The activity series has been built up by comparing the reactions of metals with air, water, dilute acids and salt solutions. This is important, students. The activity series has all the metals arranged in descending order of their reactivity, and that is arranged based on the reactions of metals with air, water. You have to remember these: air, water, dilute acid and salt solution. When we say salt solution, the displacement reactions. So, we did all those reactions, you were able to observe them and you have a good understanding. Deciding on the methods of metal extraction, identification of methods that prevent corrosion of metals, selection of metals to construct electrochemical cells according to the requirement are uses made from the activity series. You know, students, the highly reactive metals, they are usually extracted using electrolysis. Moderately reactive ones, reducing with an element or a compound. Then the least reactive or the ones at the bottom of the activity series, simple physical extraction methods. So, that is extraction process. Then we can identify how we can prevent corrosion. For example, magnesium, zinc are used to prevent corrosion of iron. Then metals selected to construct electrochemical cells. All this is possible using the activity series. Then the next one, a structure called blast furnace and the raw materials hematite. Hematite has to be spelled as Heamatite. Hematite, Fe2O3, limestone, calcium carbonate and coke are used to extract iron, the raw materials. Then gold occurs as the native or uncombined metal. Native metal or uncombined metal in nature because its reactivity is very low. and various physical methods are used to separate gold mixed with impurities. We have discussed these processes in detail. Then hydrogen, a component of very low abundance in the atmosphere, is a useful gas to man. Oxygen, so we discuss hydrogen, then oxygen, a gas present at an abundance of about 20% in the atmosphere, is useful for many tasks, including respiration and combustion. That is oxygen. Then carbon dioxide, present at a percentage of about 0.03% by volume in the atmosphere, has contributed to make the earth suitable for living organisms. It should be living organisms. Living organisms. It also acts as a raw material. It is a raw material for the production of food in plants by photosynthesis. You know the process of photosynthesis. So these are uses of gases. There is some more as the summary. I will move on to that. Increase in the amount of carbon dioxide in the atmosphere causes global warming. Now, this is something that we did not discuss, students. Now, you can remember the process of greenhouse effect. Greenhouse effect. Now, greenhouse effect is useful to us. Why? Because then only the temperature of the atmosphere will be optimal for the life on Earth. For that, we need only 0.03% of carbon dioxide by volume. In addition to carbon dioxide, I mentioned to you all water vapor, methane, nitrous oxide, all these are greenhouse gases. Now, if the amount of these gases increase in the atmosphere, then what will happen is they tend to trap more heat energy from the sun. So, because of that, the average temperature of the Earth's atmosphere will increase. That is what we call as global warming. That can lead to many other problems. We will be discussing all these in your next grade when we discuss about the biosphere, but you need to remember greenhouse effect is useful to us, but at the same time, if there is too much of carbon dioxide, that leads to global warming. That is a problematic effect. It can cause a lot of problems. According to the properties of gases, different methods are employed to collect them in the laboratory. Usually we use the downward displacement of water. Then you can remember for hydrogen, we can use the downward displacement of air. Why? Hydrogen is lighter than air. But for carbon dioxide, we use the upward displacement of air because carbon dioxide is more denser than air. So those are different methods. And in the laboratory, various methods are used to identify gases. That is also important. Burning splinter burns with the pop sound for hydrogen. Glowing splinter rekindles or relights and burns for oxygen. Whereas the burning splinter is blown off when exposed to carbon dioxide, but when carbon dioxide is bubbled into lime water, it becomes milkier. If you continuously bubble for a longer time, the milkiness is reduced or it becomes colorless again. You know the reason as well. So, those are the tests used to identify gases. So, with that, students, I have come to the end of this lesson. So, in this lesson, we discussed what physical and chemical changes are, and in detail, the chemical reactions, the types. We learned to write balanced chemical equations, and thereafter we discussed the activity series and also collection and properties of gases, their uses, as well as the extraction process. Iron extraction using blast furnace and extraction of gold. So, I am sure you all have a very good understanding of this lesson, and in the next chapter, I will discuss the questions given in your textbook. So, before you listen to that discussion, I am sure you will try the exercise first and then you can listen to the discussion.